Okay, so let's look at steady flow devices and the conservation of energy for steady flow devices. This is going to be an important and hopefully a good video for us to watch because a lot of devices are steady flow devices. We're going to look at nozzles, diffusers, turbines, heat exchangers. Steady flow just means that the properties may change from one location to another. So at the inlet might have different properties than the outlet, but they are steady in time. They are steady in time. They are constant in time. All right, they don't start at one value and then at the end, after 1 hour, they are a different value. Their derivatives with respect to time would be 0. If they're constant in time, then their derivative, ddt's, will be equal to 0. They're not changing in time, right? They're not changing in time. So our conservation of mass, all the mass coming in minus all the mass going out equals the change in mass per time. The change in mass per time is 0 for steady flow devices. Let me kind of make a note. 0 for steady flow devices. So now m in minus m out equals 0. Do you mind if I take that m out to the other side of the equation? So now the sum of all the m in equals the sum of all the m out for steady flow devices. Right? If you write that equation on your formula sheet on your note card, make a note, hey, steady flow devices. Or you can start here, know it's steady flow, and then you've got that equation. Same thing with energy. Same thing with conservation of energy. The change in energy over time, all right, not the change in energy from the inlet to the outlet, but the change in energy after an hour, after 2 hours, after 4 hours is 0 for steady flow devices. And so do you mind if I take that energy to the other side of the equation? The sum of all the energy in equals the sum of all the energy out. The sum of all the energy in equals the sum of all the energy out for steady flow devices. I can't emphasize that enough. Steady flow, steady flow. But we are going to look at a lot of steady flow devices. A lot of our devices are steady flow devices. The way that I think about it is this: if it's not collecting mass, if it's not filling up with mass, if it's not, if the mass is not changing inside of our control volume, then it's a steady flow device. All right, let's look back at this page. This page was from chapter 2. This is like the third time I've put it in here in our notes. It's that important, right? Conservation of energy. The left-hand side are inlets and outlets. The right-hand side is starting and ending, final and initial, in time, okay? Now, these could be capital E's. These could be E dots, right? These could be lowercase e's. But for steady flow devices, everything on the right-hand side of our equation is going to be 0. And so all we're doing is adding up the heat transfer in and out, adding up the work in and out. Now, this is what we haven't had before, the energy in the fluid. This is energy in the fluid, right? This is energy in the fluid. This is H V squared over 2 GZ. H V squared over 2 GZ. Okay? So let's write this equation right here. Setting this to be equal to 0. Let's write that equation here. All right, so for steady flow devices, Q in minus Q out. Work in minus work out. All right, let's see. If we want these as like power, like as per unit time, then this E right here would be m dot theta in minus m dot theta out equals 0. And aren't you glad that that right-hand side of our equation is 0, so don't have to worry about the change in time. Now, after we're going to get to unsteady flow, But right now, that right-hand side of our equation is 0. These thetas are h plus v squared over 2 plus gz. H plus v squared over 2 plus gz. See, so do you mind if I go ahead and take those to the right-hand side of our equation? I'm going to leave the q's and w's on the left-hand side of our equation, but I'm going to take the energy in a flowing fluid to the right-hand side of our equation. So it becomes q and w. I'm just going to put q plus w, but you know that in means positive and out means negative, equals m dot, let's see, when we subtract this over, this term becomes positive, this term becomes negative, so let's do out first. M dot out, h out, v squared over 2 out, gz out, minus m dot in, h in, v squared over 2 in, gz in. All right, that equation right there, if you only write one equation down on your formula sheet, write that one down. Now make a note, this is for steady flow. But that is our conservation of energy equation for steady flow. The left-hand side is heat transfer crossing the boundary. Left-hand side is work crossing the boundary. The right-hand side is energy in the inlet and energy in the outlet. All right, energy in the inlet and energy of the outlet. Okay, so that's our main equation. I might just start with that one every time. And it simplifies. You know, maybe there's no potential energy. Maybe there's no kinetic energy. Here we're going to simplify it a little bit by saying if there's one inlet and one outlet, then conservation of mass would tell us m dot 1 has to equal m dot 2. So we could kind of factor that out. And we've got this equation, Q and W equals just 1 m dot. And then like, let's go ahead and do the h out minus h in. V squared over 2 out minus v squared over 2 in. GZ, you know, change in z. So we can kind of, you know, group the potential energy together, the kinetic energy together, the enthalpy together, if we want to. So here's an equation. We could write that down, but again, it's really this first equation, that top equation. This was power. This was power, right? Q dot, W dot. We had M dot. What about lowercase? What about specific? The difference between power and specific would just be, we get rid of this m dot. It would just be delta H, delta KE, delta PE. So this, you know, here's another equation. This is the specific equation. Okay, so for steady flow devices like nozzles, diffusers, turbines and compressors and pumps, throttling valves, mixing chambers and heat exchangers, and pipe and duct flow, we can, so this is what I'm going to do, we can start with, I like to start up here, right? I like to start up here. But if we know there's one inlet and outlet, then we can go right here. If we know there's one inlet and outlet and we only want specific, we can go right there. But in general, I'm going to start with this top one, our main equation. And we've got that equation. So maybe we take that equation, we solve for some unknown. All right, we solve for some unknown. And don't forget, so can start with these energy, conservation of energy. Don't forget conservation of mass. If there's not one inlet and outlet, then we might need to really think about this m dot in and m dot out. If we've got two inlets and one outlet, the two inlets have to equal the one outlet, right? Okay, so let's talk about some of these nozzles and diffusers, turbines and compressors, throttling valves. Let's talk about these different types of steady flow devices. So what I'm going to do, I'm just going to give you in general, this is usually how we'll handle a nozzle and diffuser. You know, in general, this is how we're going to handle compressors and turbines, in general. Now, you know, the problem might be a little bit different, but these are just generally how they work. Nozzles and diffusers either increase the velocity or decrease the velocity, right? Nozzle increases the velocity, a diffuser decreases the velocity if we're in subsonic flow by changing the cross-sectional area. If we start with Q plus W equals m dot, right, because this is one inlet and one outlet, and a diffuser is just a backwards nozzle, right? You just flip the same device. So in general, we start with Q plus W equals m dot delta H delta KE delta PE. In general, there's probably not going to be any change in height from outlet to inlet. Here, 2 is outlet, 1 is inlet. 2 is outlet, 1 is inlet. 2 is outlet, 1 is inlet. Don't get it confused with like initial and final. This is outlet and inlet. In general, there's no potential energy. There is usually velocity, change in velocity. That's kind of the whole point of these nozzles and diffusers. So we will have that. We will definitely have H. In general, we're not getting work out or putting work in. In general, we're not losing heat or putting heat in, you know, unless they tell you. So unless otherwise told, nozzles and diffusers, Q dot equals 0, W dot equals 0, potential energy equals 0, and so we're left with what? We're left with 0 on the left-hand side equals m dot H2 minus H1 plus V squared 2 minus V1 squared over 2. If this is 0 on the left-hand side, I can divide the m dot out over also, and so I can say H2 minus H1 V squared 2 minus V1 squared over 2 equals 0. So, you know, that works, you know, 75% of the time for nozzles and diffusers. If you want to write that down, you can, you know, on your formula sheet, but this is for steady flow. This is for a nozzle or diffuser with no Q or W. I like to start with this. I like to start every problem with that. If it's steady flow, one inlet, one outlet, and then things go to 0. But in general, here's our what we do with a nozzle or diffuser. What if we had a diffuser and it said something about some Q going out? Then we would need to start with this, and we would need to plug in whatever Q value it told us for that one. Okay, turbines and compressors. A turbine gets work out by fluid going through it. You can think about, you know, putting like a dam, like in a stream. The fluid going through there can turn the blades, can turn a shaft. We can get work out of a turbine. A compressor is backwards. We put work in order to push blades that will push the fluid out. So for turbines, work is carried out via the shaft. For a compressor, work is carried in via the shaft. But it's the same device, just plugged in backwards. So we're starting with this because it's one inlet and one outlet. It's steady flow, one inlet, one outlet. We can start with this one. In general, 75% of the time, works all the time, there's no Q. There definitely is W. That's the whole point of a turbine, is to get the work out. And for a compressor, you definitely have to put the work in. There's always going to be H for all these steady flow device problems. If it doesn't tell you, in general, it doesn't really increase or decrease the fluid going through there. At least not very much. And probably doesn't change the height unless we're told. So in general, The change in kinetic energy is 0. Change in potential energy is 0, usually. So usually the work is m dot H2 minus H1. In general, the work, the power, is m dot H2 minus H1. So a few things to think about. 2 is always outlet. 1 is always inlet, whether we are looking at a turbine or a compressor. And remember how I do these. Work in is positive, work out is negative. So this right here, if this was a steam turbine, this work coming out, I would plug in -5. You know, it'd be -5 megawatts on the left-hand side equals, and so I could, you know, figure out that delta H right there. All right. So remember, 2s are outlets, 1s are inlets, and work in is positive, work out is negative. The way that I define, that's why I've got Q plus W. The book might do it opposite. They'd say Q minus W, and they would put minus and plus, but you see how we would both work out to the same answer. I'm putting Q plus W, and I'm saying work in is positive, work out is negative. Okay. A throttling valve is a flow restricting device. It can be called a capillary tube, a porous plug, an adjustable valve, or a throttling valve. It restricts the flow, and it causes a significant pressure drop. That's kind of the whole idea of a throttling valve, is to drop the pressure. Drop the pressure. The idea of a throttling valve is actually not to change the velocity, not to change the height, and actually it takes no work, and in general they are adiabatic. So in general the Q is 0, the W is 0, the change in kinetic energy, everything is 0. For throttling valves, the whole key is throttling valves are constant enthalpy process. Constant enthalpy processes. All right? So H out is equal to H in. How I mean, why would that help us? Why would we even use that? Well, H is U plus PV. So we can kind of expand that and say the U out, pressure out, V out of the outlet equals the U in, pressure in, V in. And so if we know a few of these, we can find another. If we know a few of these, we can find another. One more thing before we move off of this one. For an ideal gas, enthalpy is usually only a function of temperature, only a function of temperature. And so if enthalpy is constant, temperature is constant. If enthalpy is constant, temperature is constant. Okay? Okay, but so right here is really our equation that we might use for throttling valves, also called capillary tubes, porous plugs. Enthalpy of the inlet is equal to the enthalpy of the outlet, and the U plus PV of the inlet equals U plus PV of the outlet. All right, how about a mixing chamber? A mixing of 2 or more streams of fluid. Now with this one, we cannot start with this equation. Did you notice this equation? We had factored the m dot out, saying that m dot inlet was equal to the m dot outlet. But here we might have 2 inlets, 2 separate inlets right here. So all right, we're going to need our conservation of mass equation. All right. If this is a steady flow device, there's no change in mass. The sigma m in equals sigma m out. All right. This was only true for one inlet one outlet. All right, we've got to go back and start with this equation. Q plus W equals summation of all the m dot outs, H plus V squared over 2 plus GZ, minus the m dot n times each one's H plus V squared over 2 plus GZ. So there is the equation that we need to start with for a mixing chamber. Now, in general, W is 0. Q, all right, heat transfer. It seems to me like heat transfer is a big part of this. We've got cold water and hot water coming out to make warm water. Isn't there a heat transfer? There is a heat transfer, but it is internal. When we're looking at this whole conservation of energy of the whole system, yes, there's heat transfer back and forth between hot and cold, but if the hot and cold are both part of our system, then there's no Q. In general, there's no Q. It is internal. Now, unless it tells us there's some Q going out, but in general, the Q is 0. Kinetic energy is 0. So don't worry about kinetics. Don't worry about potential energy. Do you see what this really boils down to? The m dot out H out equals the m dot in H in. There we go. So that is our equation in general for a mixing chamber. So I'd take the m dot of the hot times the H of the hot, right? So for instance, I'd say m dot hot, H hot, m dot cold, H cold equals m dot warm, H warm, right? So there's one equation, and m dot, that's conservation of energy, but we also have conservation of mass, m dot H plus m dot cold equals m dot warm. So two equations that might help us plug in and solve. Okay, last one. No, not quite. Two more. Heat exchanger. A heat exchanger is just like a mixing chamber, except they don't really mix. The fluid streams exchange heat without mixing. All right? We have two methods for looking at heat exchangers. Method 1 is to treat the whole volume as one, or method 2 is to treat each fluid separately. All right? If we treat the whole volume as one, it's just like a mixing chamber. The heat transfer is internal. The heat transfer is internal, so it is 0, and it's just what we got. M dot out, H out equals summation of m dot in, H in. So that might be an equation to use. That might be helpful for us to use. So for instance, let's say we have, for a heat exchanger, we've got a fluid A that's coming in and A is going out. B is coming in and B is going out. So it's like we have two inlets right here and we have two outlets. So, we might have like the m dot A, HA out, m dot B, HB out, equals m dot A, HA in, m dot B, HB in. You see that? You see how that? We would do that if we have two inlets and two outlets. There's no need to do conservation of mass because A doesn't exchange with B, so there's only the m dot of A is just the m dot of A. It's not m dot of A different for the inlet and the outlet. All right, but if we treat them separately, so if we only look at A, then we do have some Q coming in, and it'd be something along the lines of this. M dot A, H in, plus the Q between the two equals M dot A H A out. Or M dot B, so B is the hot fluid, the heat transfer is going from the hot to the cold. M dot B H of B in minus the Q that it's leaving equals M dot B H B out. This is the same Q, same value for Q right here and here. Right? Doesn't that make sense? I think that makes sense. If you're only looking at A, then it's just going in and going out, and it's getting some Q in to it. If you're looking at B, then it's M dot H going in, M dot H going out, and it's losing Q. Right? It's losing Q. You might have to do both of these methods in order to solve for what we need. Right? Might have to do both of these methods to solve for what we need. All right, and lastly, and easiest, because I'm just going to say, all right, this is pipe and duct flow, transport of liquids and gases in pipes. Usually this is a steady flow. Usually there's not mass that's building up in the pipes. It might have work crossing the boundary. It might have Q crossing the boundary. The velocities might matter. In general, I'm just going to say it depends on the situation. It depends on the situation. And you know, all of these actually depend on the situation. And so my advice for you is to take this equation right here and start with this equation for a steady flow, one inlet outlet. Steady flow, one inlet outlet. Start with this one. And if they don't mention the change in height, it's 0. If there's not much mention about the changes in velocity, it's 0. Is there any work crossing the boundary? Is there any Q crossing the boundary? And then a lot of those will go to 0. It just is dependent on the situation. Depends on the situation. All right, so now are you ready to go tackle these steady flow device problems? That's my advice. Start with that equation for one inlet outlet steady flow device. Study these heat exchangers and mixing chambers, because that's the one that is different. That's the one that has 2 different inlets and possibly 1 or 2 different outlets. That is different. But most other ones, you can start with this conservation of energy equation, plug in what you know, take to 0 things that we can neglect or that it doesn't mention. All right. Good luck.